All right, recording is rolling. It's Wednesday, November 15th. I guess remember we're on this slightly shortened per period schedule. So got slightly shorter days today. Main focus today is going to be this coefficient of restitution lab. Remember, this is a way to quantify how bouncy is the collision. I'll do a quick review to you guys through the posters and then set up the lab table and graph, and we'll do that. Okay. And so remember, today's the last day of an interim. So check this class and all your other classes. Make sure you're not missing any assignments. You've turned everything in. There's a few things we've got going on this week. I'm just accepting everything up until the break, right? Including, and this is just one of the things, is this momentum half page. A lot of you guys have already turned this in, but if you haven't, make sure you get this in before you leave for Thanksgiving break. Okay? Now, the last grade that's going to go on this interim is going to be this coefficient restitution lab that we're going to do today. Right? Tomorrow, I'll do a review with you guys on both energy and momentum for the quiz on Friday. You guys remember the quiz on Friday? We have the desks and rows. It's going to be an in-class quiz. It'll be closed notes, energy, momentum. So we'll do a review tomorrow. I think if you've been paying close attention and so far in this class and think about what you're doing, then I think you're going to be all right. Do a review. Okay. All right. So let's see, what is coefficient restitution? And how are you going to quantify this? Okay, so we got here. We got momentum. You guys remember? Oh, okay, so that's what we've been doing last week and a half. Momentum is mass times velocity. This is a vector value. It's involved in collision physics, and it's conserved within those collisions, right? Within closed systems specifically, right? So if there's no external force, right? So here's just a general collision, and momentum is shown conserved, right? So we have two separate objects, each with their own mass and velocity, and they boing, collide, and then what happens, right? Well, there's like a bajillion different possible outcomes from this collision, depending on the material properties, right? Like if they're both made of soft clay, maybe they stick together, kind of like this next poster. Ooh, stick together, right? Or if they're like Newton's cradle balls, maybe they bounce off each other really well, like boing, boing, boing. That's really bouncy right there, right? It's probably bounces good. Or maybe they're like half-played tennis balls, right? Boing, like bounce off, but not very well. Right? Regardless of which of those scenarios it is, right? This statement right here is always, always, always true. Right? Momentum is always conserved before and after the collision. Right? Then we can look at different kinds of collisions, right? So at one extreme is perfectly inelastic. That's like the balls of clay sticking together, and the equation starts the same, right? You got mass times velocity that's before the collision, right? Add up, right? And then after the collision, well, you can modify a little bit. I actually think this one looks a little simpler because it's one giant mass given at one common final velocity. Okay? Now, the other extreme kind of collision you could have is perfectly elastic. That's like perfectly bouncy. And from a physics point of view, what makes perfectly bouncy is that not only is momentum conserved, which is true for any kind of collision, but also this right here is conserved, kinetic energy. So before and after the collision, if you add up all the kinetic energy bits, it also equates. Remember, that's only for perfectly bouncy. Okay. Now there is a result from the system of equations. Here's the general solution to that. Here's the post-collision velocity of one of the objects is this crazy looking fraction. Right. Now I'm not going to expect you to memorize that, but it's good to know that's there. That's how you would solve that. If you take physics in college, let's say you're doing a science major, there's a good chance you're going to get this question and be expected to solve it from scratch. Well, there's the answer. You have that from high school. Okay. Here's a big old. You guys haven't seen this one yet. Here's a big old table of types of collisions. Here's perfectly boingy, here's perfectly sticky, and here's just somewhere in the middle, right? So we got like a whole spectrum here. And for fun, I throw on explosion, which is kind of like a reverse collision. You guys have seen a couple of explosion type questions, right? Or even like a magic school bus, throw the baseball and the pitcher gets kicked back the other way. That was kind of a version of this last part too, right? So regardless of which of those scenarios, right, momentum is always conserved. This is just copy pasted all the way down, right? Sum of momentum before and after the event is always the same, right? Now, kinetic energies do different things, right? So for perfectly elastic, it's conserved. Perfectly inelastic, it always decreases. And in general, it'll decrease. Could be the same, but that would just bring it back to perfectly elastic, right? And then for an explosion, the kinetic energy will be shown to increase, right? But that makes sense, right? Because energy is being added to the system from that explosion. Like if you, case of the magic school bus clip, if you throw a baseball, well, now you're adding energy to the system, comes from your muscles, right? is where that extra energy would come from. Okay, so then how would energy be shown to decrease? Because I thought energy was conserved from like 2 weeks ago, right? Well, energy is conserved. It's just that this mechanical energy, this kinetic energy would decrease. And then you say, well, where those extra joules go? A really common explanation is like a permanent deformation. Like if this is soft balls of clay, that there's a lot of force times distance that goes into deforming those objects. Okay, and then that's a little bit of review. That's a lead-in to this right here. Is now we're on the spectrum from perfectly inelastic, that's perfectly sticky, to perfectly elastic, that's like perfectly buoyancy. What's a way you could quantify where you are on that spectrum? And that's what this is right here. So coefficient of restitution, that's just a fancy physics phrase for like where are you on the spectrum between perfectly sticky and perfectly bouncy. So coefficient of restitution is defined as this. It's a ratio. What's the post-collision difference in velocities compared to the pre-collision difference in velocities, right? I'm showing absolute value bars just to turn what would be always a negative number to what always a positive value, right? And it's bounded between two numbers, like there's two theoretical limits on those, right? So perfectly sticky, if these bounce, perfectly inelastic, if they stick together, what's the post-collision difference in velocity if they stick together? Zero, right? I have it's this right here. Here, it's right here. This is it. Right? It doesn't bounce at all, right? There's so then if this is zero in the numerator in this fraction, then the whole thing would come out to zero, right? So that's one extreme. What if they're perfectly bouncy, like Newton cradle balls, like boing? What does this ratio always come out to? It always comes out to 1, right? Right. Yeah. So for example, if you dropped a bouncy ball and like from some height, and you're considering like the ball versus the entire Earth, right? Let's say you're bouncing off the tile floor, right? And it boing rebounds to the exact same height that it started. Well, that means that the rebound speed is equal to the crash speed. So these speeds are the same. Yeah, and this would come out to a 1-to-1 ratio. Right? But it would take something that was perfectly bouncy for that to happen. So maybe more realistically, the coefficient of restitution is going to be somewhere between those two. It's going to be somewhere between 0 and 1. It's like 0.44, somewhere between 0 and 1 to tell you how bouncy something is. And that is what I'm going to have you guys do today. Now, you guys are going to do this version of it. That's the story I just told you, right? You bounce a ball off the floor. So you drop the ball and you let it rebound to some height. Right? Now, those heights, there's enough information embedded in those heights where you can, in principle, do this calculation, right? Which is what you guys are going to do today. Okay? Right? So really, coefficient of restitution is defined as this. What's this rebound speed compared to this crash speed, right? Because boing, right? There's a rebound speed and a crash speed. Now, if they're the same, that would be 1. That's perfectly bouncy. If the rebound speed is 0, it sticks to the ground. Or okay, then this would be 0. Right? So 0, 1. But more realistically, you'll just get two different heights, right? Which is going to correspond to two different speeds, right? Now, what is the connection between the speed, like either rebound speed or crash speed, right? And the height, either rebound height or drop height, right? Well, that goes back to, you could either go all the way back to kinematic days, you guys remember those 3 kinematic equations, or more recently, let me find, they got my energy posters, let me find the Galileo poster. Here's Galileo. You guys remember Galileo drops the ball from the top of the tower, right? And a question could be like, well, how fast is it going at the bottom? Remember the math cancels out. That was actually what Galileo was showing back in the day, right? But how fast is it going at the bottom? Right? One way you can solve this is with conservation of energy, potential energy at the top, kinetic energy at the bottom. And this is always the solution to that, right? Once you cut through the algebra, it's mass cancels, times 2, square root, boom. It's always square root 2gh, right? This is a really classic example to know from a physics class, right? Square root 2gh is going to be the crash speed, right? Well, you could say a similar thing for the rebound speed. Right? It's also square root 2gh, but playing off the rebound height. So if you divide these two square root expressions, the 2g cancels out. Right? So the gravity field of the planet ends up not mattering. Right? As long as there is gravity, it doesn't matter how strong the gravity is. Okay? So you could do the same experiment on the moon, and I bet you get like the same results. Right? If you had a tile floor on the moon, right? So the square root of the ratio of the heights is the same thing for coefficient restitution, and this is the version you guys are going to do today. So what if you, let's run an example. What if you take out a meter stick and you drop it from 100 centimeters and it boing rebounds to what's a good number? How about 25 centimeters? Right? So you drop it from 100 centimeters and it boing, rebounds to 25 centimeters. Okay. Guess what would the coefficient of restitution be for that scenario? Who's gonna figure it out? Drop it from 100 centimeters. It boings back up to 25 centimeters. What is 25 over 100? It's like a quarter, right? And then what's the square root of 1 over 4? It's like 1/2. Ah, okay. So if something rebounds to a quarter of its original height, what that means is that the ratio of the speeds, rebound to crash speed, is 1/2, which is coefficient of restitution, would be 1/2 for that scenario, right? Is that it? Side note here, I do have a new poster. I'm going back to energy stuff, right? Here's the alternate way you could have shown the same thing for middle stuff, right? Is go back to kinematic case. Here's the energy thing. We just kind of went through that, right? But here's the kinematic version, right? If you want to figure out, so it's the relationship between like this maximum height and this like speed at the bottom, right? It's square root 2gh either way you do it. Right? Here's like the really old way of doing it. Here's the way we did it like a couple weeks back. All right. So now let's bring this to see what you guys are doing today. Right? You guys have a half page in front of you. You guys see that half page, blank half page? Right. So copy down this table right here. Right? You guys got rulers. You guys gonna draw some straight lines for a table. Okay. So you're gonna do different trials. Try different drop heights. You guys have a bouncy ball in yes, right? You guys got a bouncy ball? Okay. So take that bouncy ball. The question is, well, how bouncy is the bounce ball off this tile floor, right? Coefficient of restitution. So try different drop heights. Right? Oh, here's a column for drop height. I said centimeters here. You could do meters if you want. So centimeters or meters. Right? Same thing for rebound height. Ooh. So you got drop height and rebound height. You can measure those with meter sticks and your teammates. Boom. Right? Get different numbers, right? And then calculate what is the coefficient of restitution based on that. Right? Now, after you guys get this table of data, you probably get it. I wonder if it's the same coefficient of restitution regardless of the drop height. Right? You guys are about to figure that out. Okay? Graph drop height versus rebound height, and what do you guys think that graph is going to look like? Right? So see how we're doing on time in here. We got till oh, all right, yeah, we got about 20 some minutes of class. I think it's a perfect 20-25 minutes. I think it's the perfect time to do this lab. Yeah, so try different drop height, rebound height, fill out the table, make this graph, right? Rebound height versus drop height, see what that graph looks like. Scale the axes, label the axes, and then when you're finished with that, turn that into the grade tray, and that will be the last grade of this interim. With that, I will close this recording.